Good day, ladies. So today we're going to look at the last topic on our Unit 1, Module 1 topic, and that is kinetic theory. So we're looking at specific objectives 8.1 to 8.4, some of which will be covered in this actual presentation, some of which you will get to do as calculations. Those of you who are physics students, some of this would be familiar territory for you, and the calculations should be fairly easy to follow. Those of you who've not done physics, fear not. This is not only for physics students, but it is an important part of our chemistry. The calculations are fairly straightforward once you understand how to manipulate the equations. So what is kinetic theory? Excuse me. So kinetic theory looks at all substances. The definition really, or the understanding of the theory, is that all substances consist of minute particles, and these particles can be any of the ones that we've become familiar with, your atoms, molecules, or ions, which are in a state of constant random motion. And this last part here is critical to when we start to talk about gases, which we will spend some time discussing today. So we're understanding that the overarching or view of kinetic theory is that our substances are made up of small particles, and these particles are always in motion. So why do we study kinetic theory? Why do we care? So as chemists, what is important to us is the behavior of matter. So we study matter in terms of what is matter made of, which is why in Form 3, we started looking at physical and chemical properties of matter. We start looking at our atoms and our ions, and then we started looking at the atomic structure to get an understanding of what is matter made of. And then we started looking at the properties of matter, whether it's an ionic compound, whether it is a covalent compound. But there's another aspect of matter that we really need to understand. And in this case, when we're looking at kinetic theory, we are looking at the properties of matter as they exist as solids, liquids, or gases. Because when we study this matter, we are able as chemists to manipulate matter. And that's basically what we do as chemists all the time. We understand matter. We understand how matter will behave at certain temperatures. We understand how matter will behave if we mix it with something else in a chemical reaction, for example. So a kinetic theory, because again, we are looking at the fundamentals that our matter is made up of particles that are in constant random motion. How do these properties affect what we can do with a solid, a liquid, or a gas? So we're going to focus today on the gaseous state, and that is your reference to Chemistry in Context, chapter 4.4 to 4.6. 4.6 actually looks at I believe the methods of determining molecular mass or molecular weight for volatile compounds and liquids. It is not stated explicitly in your syllabus. However, if you look at the CXC study guide, they have overlapping information. And I'll share that with you for those of you who don't have the CXC study guide, but your Chem in Context refers to it in 4.6. And while it's not stated explicitly in your syllabus, the study guide does make reference to it, and it's something that you probably should learn. So as we look at the gaseous matter, we're understanding that we're looking at the kinetic model that relates the behavior of gases. Remember, we're trying to understand how matter behaves under very specific conditions. And so we'll find ourselves talking about ideal gases, and by extension, we'll also look at real gases, because these gases have specific behavior under conditions of temperature and pressure. So at the end of this module, certain parts we will break up. You should be able to state the basic assumptions of the kinetic theory with reference to an ideal gas. So there are many aspects of our kinetic theory, the model of our kinetic theory, our kinetic model of gases. And our first assumption, as we had seen before, is that it is a collection of molecules that are in constant random motion. So this fits right into our kinetic theory that our matter is made up of small particles that are in constant random motion. We understand using our kinetic model that our molecules are small and the volume of the molecule is negligible compared to the volume occupied by the gas. Now, this is highlighted in green, as another one will be, because later on, as we start to look at our ideal gases, we would look at these two properties that are highlighted in green. Now, when we say that our molecules are small, under the assumption that in an ideal gas, the molecules are small, and the volume of the molecule is negligible compared to that occupied by the gas. So they're sometimes referred to as point masses. So here's this analogy. If you, for example, you are a molecule and you are standing in the Queen's Park Savannah, for example, the volume that is occupied by you relative to the volume that is occupied by the Queen's Park Savannah. So if you are the molecule and the volume that can be occupied by the gas itself is the Queen's Park Savannah, you can see therefore that in this similar fashion, you being a point mass, your volume relative to the volume or the space that the Savannah takes up is much smaller. So this is where we say the volume of the molecule compared to the volume occupied by the gas is negligible. So that is in comparison to, for example, and my simple analogy here, if you are standing in a bathroom stall in school, for example, you will not be considered a point mass because your volume, the space that you occupy relative to the space of the toilet stall, is very large. You will occupy quite a bit of that toilet stall space. So in that case, you are not going to be referred to as a point mass. So these are the ways that we can understand the relative size of the molecule relative to the actual volume that it will occupy, that the whole gas will occupy. So hopefully that gives you a little scale reference. Of course, we are much bigger than an actual molecule will be, but it's a scale reference. Hopefully that makes sense. So the other assumption is that intermolecular forces between the particles, between these molecules of gas, are negligible, that they are non-existent. And so we hope, or we understand that molecules will exert no force on each other. They don't interact with each other. The molecules are themselves isolated from others, and there is no interaction between one molecule and its neighbor. Now, this again is the assumption of ideal gases, right? Ideal meaning in a perfect scenario. So these two things, as I've mentioned before, because they're highlighted in green, these are the assumptions that we will revisit when we start looking at ideal gas behavior in a little more detail. So some other assumptions of our kinetic model is that collisions between our molecules are perfectly elastic. That meaning that if two molecules hit each other, there is no loss in kinetic energy. The exact same amount of energy that they've hit each other with is the exact same amount of energy that they will move in their opposite directions after the collision. So they are perfectly elastic and there's no loss in energy. We have that the pressure of the gas is due to collisions between molecules and the walls of the container. This is something with which you should be familiar, that any force that is exerted on the surface of the container by the particles in the container, that would be the pressure. So the more collisions that we have, the higher the pressure that that container will have. And our last one is that the kinetic energy of the gas is proportional to the temperature of the sample. And this is something that is almost intuitive to you because you are understanding, or at least I hope you remember, that as we raise the temperature of our gases, our kinetic energy will increase and the particles, of course, will move a little bit faster. So these are the basic assumptions of our kinetic model. And depending on what behavior we are looking at with our gases, these assumptions fit different spaces, if you will, in terms of explanations. So what, again, we will focus on are assumptions 2 and 3 for the sake of our look at ideal gases. So syllabus objective 5.3, and I've skipped 5.2 a little bit, I think, is asking you to state Boyle's law and Charles' law include graphical representation. So I'm just going to go through this because really and truly it's fairly straightforward in terms of what the laws are. You can look in your textbook, or you can look in your, well, use some of the definitions that are presented here. So in at the end of this, you should be able to state what Boyle's law and Charles's law actually are. You should be able to draw graphs to represent Boyle's law and Charles' law, and you should be able to do some calculations using both laws, Boyle's and Charles, as well as the combined gas law. So let's have a look. So there are three major laws that govern the behavior of gases, and those are Boyle's law, Charles' law, and Dalton's law of partial pressures. I believe Ms. Smart would already have introduced you to Dalton's law of partial pressures. It is in your textbook in this chapter as well. And so we're making some assumptions that our absolute zero is 0 Kelvin, or negative 273.15 degrees Celsius. And this is the temperature at which our gases have zero volume. And this is very important because this comes back to our point mass, where the volume of the gas, sorry, the volume of the molecule is negligible compared to the volume of the gas. So Boyle's law, for a fixed number of moles of a gas at a fixed temperature, the volume of a gas is inversely proportional to its pressure. So we have this relationship where P is inversely proportional to 1 over V, and the product PV is constant. Again, as I said, the alternative references for definitions will be your chemistry in context. Whichever definition sits in your brain fastest and easiest, that's the one that you should learn. So according to the study guide, CXC study guide, these are your graphs for Boyle's law, showing Boyle's law, where the pressure is inversely proportional to volume. And of course, volume is directly proportional to the inverse of pressure. Please note the axes. Please note where your, for graph B, that your line is running through 0 for both of them. So your Charles law says that volume is directly proportional to temperature at a constant pressure. And we understand that when that is drawn on a graph, there are two ways that this can be drawn. One where temperature is in Kelvin, and we go to absolute 0 Kelvin on the left-hand side. Or if temperature is in degrees Celsius, you have to take it across the y-axis to the negative 273.16. Now, please pay attention to this, because depending if you have this type of question, if you are asked to complete a graph where the unit on the x-axis is not given, then you decide whether you're using temperature in Kelvin or degrees Celsius. If the axis is given to you, then you must include the correct cross overlap. Now, I would suspect that if they are giving it to you in degrees Celsius, then you would see the y-axis will almost bisect the x-axis, and it'll be a kind of hint that you have to go across it and mark the line. Otherwise, you know, you just do your right quadrant. But pay attention to the unit on the x-axis always. The text shows you the two x-axes placed on the same graph, which is an interesting way to present it, basically hedging your bets. None of these are wrong. It's just please remember it and draw it correctly. So your combined gas law is, of course, P1V1 over T1 is equal to P2V2 over T2. This is the combination of Boyle and Charles. So there'll be a few more examples for you to try. I would suggest that you have a read of the sample questions that are in the text, and more will be posted for you to attempt as practice. So the last equation, which is another equation that is derived from Charles's and Boyle's law, is what we refer to as the ideal gas equation. And that is where pressure times volume is equal to the number of moles N, small n, not big capital N, the molar gas constant R times T, temperature. And this is the equation that all ideal gases will obey at all temperature and pressure. And this is very important for us in understanding the behavior of ideal gases. Please note the units. In most cases, you will be given the units in R as joules per Kelvin per mole, because that tends to be, I realize, the way that they give CXC questions. However, for the sake of examples that you may find or examples that I may give you, please note that if the pressure is given in atmospheres, the R that you would use is the 0.0821, right? As I said, most questions will give you the volume, sorry, the pressure in kilopascals, and then your R would be that 8.31. But just an FYI, don't mess it up because you've not paid attention to your units. So again, these are some examples that this is one set of calculations that I would like you to try. Ideally, if you were in school, we would sit and we would do it now, but please make note of it because these are questions that you would be expected to have the answer for. Hint, hint, hint. And so you make a note and do the questions. Now, it is very simple to manipulate these equations because it's a simple matter of plugging your PV equal nRT, keeping track of your units. It is absolutely critical that you keep track of your units because you do not want to have something in meters cube when it should have been in decimeters cube, and you know everything goes haywire afterwards. So this is your Dalton's law of partial pressures. It is not needed for what we need to talk about here today, but it is something that I'm sure you would have come across when you were doing equilibria with Miss Smart. If you've not done so yet, it will come up. So please make note of it. So here we get into our discussion of real gases versus ideal gases. What is a real gas? What is an ideal gas? And this is really very, something that is real is something that exists. Something that is ideal is something that is the perfect representation of that thing under perfect conditions. So your real gas is one that does not obey Boyle's law and Charles' law. So in real life, scientists have shown that most gases do not obey Boyle's law and Charles' law directly. It's not possible. And that's because these gases were derived using the kinetic theory and assuming ideal gas behavior. Now, what does that mean for us? So you are expected to, according to your syllabus objective, explain the differences between a real and an ideal gas, qualitative treatment only, what are the conditions necessary for a gas to approach ideal behavior, and graphical representations of the real and ideal gas behavior. So after this section, you should know the differences between a real and an ideal gas. You should be able to state the conditions under which a real gas will either approach or deviate from ideal gas behavior. You should be able to explain why they deviate and interpret a PV versus P graph. So just a recap on our assumptions for the model, and we come back to these two things, that we are assuming under these conditions that our gases, being ideal gases, are small and have negligible volume, and they do not exert a force on each other, meaning that the intermolecular forces between the particles are negligible. So we are basing our explanations moving forward on these two things: the relative size of the gas to the volume occupied by the molecule, and whether we have intermolecular forces. So one of the things you can be asked to do is sketch the graph of PV against P and PV versus T for a fixed number of moles. Now, I would suggest to you that you pause the video here and you sketch the graphs based on how you interpret this ideal gas equation. If we were to plot PV versus P pressure or PV versus T, what does that graph look like if N is constant and, well, R is a constant value because it is the molar gas constant? So pause the video, take a few minutes, sketch the graph, and then we move on. And then you could restart the video and move on. I hope you are actually doing so. If you're not, there's nothing I can do about it. All right. So this is what a graph looks like for PV versus P. Now, for an ideal gas, you will find that the product PV, pressure times volume, remains constant at all pressure. And of course, this graph, because it's plotted against P, is at constant temperature. We find, though, that for a real gas, there are deviations where the product PV tends to vary at different pressures at a constant temperature. So a PV against P graph is supposed to have just a straight line where your PV product is constant at all pressure. A similar graph will occur if you were to plot PV against temperature at constant pressure, because again, your ideal gas will have a constant product PV. It will have constant pressure times volume at all temperature. So this is what our graph would look like, PV versus P. Now, a gas behaves ideally if it obeys the ideal gas equation at all, emphasis on all temperatures and pressures, which doesn't happen in real life because that's not how real gases behave. Your real gases will deviate from the ideal gas behavior because of things that we've mentioned before based on our model of the gas. So under what conditions will we have a real gas approaching ideal gas behavior? Remember that we said, trying to go back the slide, okay. Remember that we said A real gas will deviate from ideal gas behavior because the gas has volume and it has intermolecular forces. So if a real gas now has to approach ideal gas behavior, what needs to happen in terms of its volume and in terms of its intermolecular forces? What factors will affect the relative volume of the gas, and what factors will affect the intermolecular forces of the gas? Under what conditions can we influence the intermolecular forces? That might be the one that might be easier for you to think about now. What conditions will influence the intermolecular forces? So here we're seeing that a gas molecule in the real conditions has intermolecular forces, but can you think about under what conditions can we remove or reduce these intermolecular forces? Similarly, we're seeing that a real gas has a small but finite volume, meaning that the volume of the molecule is large relative to the volume of the gas in the container. So under what conditions can we change the volume? So this is what I need you to be thinking of as we move forward. So under what conditions of pressure and temperature do we get a real gas to approach ideal gas behavior? How do we reduce intermolecular forces, and how do we reduce its volume relative to the volume of the gas? So in your text, there is a question, quick question, 6th edition, quick question number 9, that shows a similar diagram to this one. And I would like you to take the time now, yes, pause the video, and take some time to interpret the questions or answer the questions that are asked in that quick question number 9, because it is asking you specific questions about nitrogen in this graph. So when you're done with those questions, please now take some time to summarize what was proven by the questions. And again, this is in terms of what do we see as the product PV. Now remember RT, while this is PV over RT, RT is constant. So what are we seeing about PV for this gas nitrogen as pressure is changed? In terms of, well, temperature, and it was, sorry, it wasn't in, it's not constant. Anyway, yes, constant temperature. PV over RT will be, PV over RT will change based on the temperature that is on the y-axis, that is on the graph. My bad. Anyway, sorry. Just take some time and do quick question number 9. Summarize what was proven, and then once you've done that, move to the next, continue with the video. So check your answers. So what we're seeing based on that graph is that a real gas will approach ideal gas behavior at high temperature and low pressure. Now, if we were to revisit the graph, this is what we're talking about. Approaching ideal gas behavior is going to look like, how flat does that graph look? How closely does it resemble the straight line that is the ideal gas line? This is what we talk about approaching ideal gas behavior. How close is it to the straight line? And we're seeing that it is closest at high temperature and low pressure. So that our real gas approaches ideal gas behavior at high temperature and low pressure. At high temperature, We understand that our particles are going to be moving more quickly because they've gained more kinetic energy, and this high temperature will cause the intermolecular forces to be broken, so that intermolecular forces become negligible and particles are able to move almost independently of each other. Similarly, at low pressure, we understand that there is a larger volume in the gas because it's not compressed into a small space. At low pressure, the gas will occupy a higher volume, and so the distance between particles is going to be larger, and so they're not going to have the opportunity to form intermolecular forces, and the volume of each gas molecule relative to the volume of the gas is going to be very, very small. So when we look at this high temperature and low pressure, using things that we've already learned, it allows us to make sense of how do we get our gas to approach ideal gas behavior. And similarly, your real gas will deviate at low temperatures and at high pressures for the exact opposite reason. At high pressure, think about what's happening to your particles. Think about what's happening to the volume of the molecule relative to the volume of the gas. Similarly, at low temperature, what does that mean for the kinetic energy? What does that mean for the intermolecular forces? So as we wrap up this section, we can just look very closely at different types of gases and how they behave. This is at constant temperature, but different pressure. So we're seeing that there are deviations, what we refer to deviations above and below the ideal gas line. And real gases, nitrogen, methane, hydrogen, and carbon dioxide, deviate considerably from ideal gas behavior. They all, however, have a point at which they behave ideally. Can you see when that is? At which point do all of these gases behave ideally? Remembering that our real gases have finite volume, real gases have intermolecular forces, and the external pressure is increasing because of all of the different forces of attraction that is, this is something else. Within each gas, as external pressure increases, the volume of the molecules becomes significant. This is increasing external pressure, and the intermolecular forces increase. So we're seeing, right, as the graph, as pressure increases, they have the highest deviation from ideal gas behavior, which is on the top right-hand side of the graph. But the question that I had asked is, under which condition do they all approach ideal gas behavior? And you should see that all gases approach ideal gas behavior at 0 atmospheres of pressure. So at 0, they all are on the ideal gas line. And then as pressure increases, there will be the variations or deviations above and below. We're not expected to explain the deviations above and below, but we are expected to, just to recap, explain the differences between real gases and ideal gases, the conditions necessary for a gas to approach ideal gas behavior, the limitations of ideality at high pressures and low temperatures, and use graphs to represent. So this ends the gaseous portion of your kinetic theory, and there will be some questions posted for you to do as calculations and practice. All right. Please be safe.